To first acknowledge my co-authors here, or co-presenters, I should say. There is PhD students and senior researchers in my lab who helped me a lot to develop this presentation here, especially contributing experimental results, which I'm going to show you in the next couple of minutes. For the outline of my talk, you can see I would like to talk a little bit about the history, about the development of passive three-phase rectifier systems, and then about the Vienna Rectifier more in detail, and then a little bit comparatively evaluate the topology against competing approaches. And finally, and this gave me quite a headache in the preparation of this presentation, about the beyond, so this little spaceship going up there. And what the future of power electronics might bring. Just 2 slides, if I can manage to keep the time. Ong is quite concerned about this. You can see here is the 34 slides, and we just managed to cover the first one. But let's see how we can manage. So history, passive three-phase rectifiers, how did those originate, and then the Vienna Rectifier, and then APEC 1998 here. So you can see here, this is the important date. It's 1898, so 120 years ago, roughly. And Vienna seems to be a good place for rectifiers, because this was published here in a journal, which was a weekly journal at this time in Vienna. And you can see here the topology of this passive three-phase rectifier. I mean, it was only valves and discharge tubes available at this time, so no solid-state power devices. But the people really managed to analyze all the details of the operation of those passive rectifiers. So roughly 100, a little bit more years afterwards, I was here in 1993, and the 23rd of December, my wife not really being happy, me writing a patent application at this time of the year. But I managed to file that patent just before Christmas, and this was on the Vienna Rectifier, which is a three-phase topology. You can see the mains here and here the power stage, and we will discuss a little bit more on how this converter works. Anaheim, 20 years ago, you see it's an isolated version of this topology with an output stage here, which is isolated, just using 2 more switches. Is kind of simple, but also limited in controllability, but certainly nice to analyze, and at this time it was good enough to do a PhD. Okay, let's go further here, and I need to bring my slides forward here, which seems not to work. Ah, yeah, here we go. The topology derivation of the Vienna Rectifier. This is what I would like to show you, and then a little bit of the basic function, and finally the hardware demonstrator. So what performance could you really expect from this topology? If we do a passive three-phase rectifier, we have here 3-phase mains, and this is the mains voltages, phase voltages, and you can see this is here the line-to-line voltage envelope, and it's always the largest line-to-line voltage driving the current, meaning that you have here a current flowing in this diode and here returning via this path, and this middle path here is really left without current. So this is one of the big disadvantages of this passive approach, because you can see we have gaps of current here, 0 current, meaning low frequency harmonics, and we don't have really a control of the output voltage. So this is some key disadvantages. There is the simplicity as an advantage, but this is a key disadvantage. Now, for the Vienna Rectifier, you can see this is just the input stage passive rectifier. We need to have means to control this node, to really modulate the voltage at this node, and then we have a chance to really control the current in the phases here. And the most simplest approach is here to just connect switches to the midpoint of the output, which is a capacitive midpoint. And you can do this in each phase. You have a bridge and a phase symmetry of your topology, and you could also find other topologies here of the bridge legs which would do you the same. So the modulation of the voltage, this is the key issue here which we want to achieve. You can see here it's working nicely. If the current is impressed by the inductor, it goes to the positive bus, and if I turn on the switches here, it would be increasing, and then I turn it off, and then it would be demagnetizing. The inductor would be demagnetizing, and I could ramp down the current. So finally, I can nicely sinusoidally shape the current, which is what I want to have. I mean, I'm kind of limited here with the current direction, of course, in the voltage formation, but if I'm aiming for an ohmic behavior, voltage and current would be in phase, and this is not really an issue here. So this nicely works. Now what we need to generate at this end of our inductors here, these inductors connected in series, you can see here, this is the mains voltages, this is the voltages which we generate, and we just have a little phase shift between the two voltages, that some voltage is left across those inductors here, and this then would impress us a sinusoidal current. This is just here drawn in a very schematic form, but we will just see it on the next slide in more detail. So this is the key idea, and this allows us to really shape the current, and if we can shape it, we can give it a certain amplitude, and if we have an amplitude, we also can control the output voltage because we can feed more power or less power to the output. You can see here more of a detail about this voltage generation. I mean, of course, we cannot generate the sinusoid, but we can generate something which is close. And the reason being is that you can see we can switch between a positive bus and a midpoint, or if the voltage we need to generate is negative, then we can switch between 0 and minus. So altogether we have 3 levels in each phase. And if you consider the 3-phase system in total, then you would find that you would find 9 levels here of voltage, which are very close to this ideal sine wave shape. This allows you to have a very smooth current shape here, and you can see there is, of course, a ripple, but the ripple is relatively small. How to control the system? Typically, you would do a two-loop control. You need an output voltage control here. The output voltage defines how much of current you should inject, and this is then measuring the current. You would run to a current controller, and this finally would define the switching of your system here. There is a little bit of speciality of this circuit because remember we have a capacitive midpoint of the output voltage, and we need to stabilize or to balance this midpoint. This is what we can do because our topology here offers redundant states, meaning you can see if I turn this switch on here and if I return the current through these 2 diodes here, I have a certain voltage which is here existing between the phases, and my current to the midpoint is positive, you could say. And I can achieve the very same voltage situation with a different switching state here, but the current is negative then. So the topology offers really enough degree of freedom to balance this midpoint, which today is very well known from 3-level topologies, also in medium voltage applications. You need to do EMI filtering. So it's not just the inductors here in front, but here the EMI filter, and you can see this is the share of the volume you would have. Something like 2/3 of the volume would be EMI filter and boost inductors, and the rest here is really 33% roughly for the power stage and the heatsink. This is a demonstrator system. It has 10 kilowatts a liter or 160 watts per cubic inch, you could say, and it's operating at 250 kilohertz here, and this would be this part you see 2/3 roughly being the filtering and the EMI attenuation, and the rest here being the power stage and the output capacitors. Current, very nice, 800 hertz operation like you would have on an aircraft, for example, more electric aircraft, and the THD of this current, it's the yellow curve here. The upper curve is the phase voltage. You will find it to be just 1.6%, so well below this 3% limit, which you typically have to fulfill on aircraft. We built several stages here. The numbers indicate the switching frequency. So you can see if you switch at the megahertz, for example, just to push it to the limit, you would find something like 15 kilowatts a cubic inch or something like 250 watts 15 kilowatts per liter, and something like 250 watts a cubic inch. So this can be done. I mean, efficiency would be a bit lower then, but this gives you an idea. And it's interesting because people always think the power density is kind of linearly related to the switching frequency. But if you look at this diagram carefully here, we have certain power density at 100 kilohertz. And if we go to a megahertz, we are roughly doubling the power density. So it's not going up by a factor of 10 on the system level. Now, comparatively evaluate. This is always important, and you see the 3-level topology, of course, being an excellent choice, and the 2-level topology, let's compare it. This is the 3-level topology, and we need to look at the voltage at this node because this finally defines the switching frequency ripple which we are facing here in our inductor. And you see this nice approximation which we already discussed. For a 2-level topology, we would be switching between plus and minus here, which also gives us some extra levels here if we have a 3-phase system, but still there is much more of a deviation here, which finally gives us a much higher ripple of the current for the same inductance here at the input compared to what we would have for a 3-level topology. So this is definitely a main advantage which we would have. Power density, 12 kilowatts per liter here for the 3-level and 8 kilowatts a liter. So you can see the relative difference here. But of course, there are barriers. I mean, if you look at this topology, it's clearly a unidirectional topology. And there is no isolation, and it's boost type. So the bidirectional feature we could easily implement in adding switches here to the diodes, and this would then be a bidirectional system clearly, but still we have boost type and no isolation. So we need to think of buck type, and I would like to show you how you could achieve this, and it's a pretty simple consideration, I hope. And we start again here from our diode rectifier. And you remember that we had this middle phase where we had no current. So why not do a stage here, a bridge leg with an inductor and a selector here, such that we could inject current here. And if you can manage to do this, and if you put the load, which is a constant power load, you can show that you can achieve sinusoidal current in all 3 phases. So the topology would look like this. You see, this is this injecting stage here, and a buck converter caring for the constant power operation here. And then we should finally get sinusoidal current at our input here. Check it out, build a prototype, build a demonstrator system. Here you see this is a 60 watts per cubic inch system, and the important number here is not the power density, but it's the efficiency. It's 99.1% efficient. You can see very nice current shape at the input. Here we have the phase voltages, and here you can see this is the efficiency curve, very flat. Silicon carbide MOSFETs is what we have used in silicon carbide diodes, so very nice performance you can achieve. It's a buck type system. This is something which was coming up in the beyond thinking of this, before this talk, 1 of 3 rectifier, meaning 1 out of 3 legs is modulated. You are already familiar with this topology here, and we are injecting here a current always in the middle phase. So why have an extra stage here? Why not install the switches here and only modulate this middle phase here and keep the switches of the 2 other phases constantly on within 60 degrees, so 1/6 of our fundamental interval. And the buck stage, again, caring for the constant power operation, but not only, we modulate this voltage here with a 6-pulse shape, such that the current in the other 2 phases, in this phase, is also shaped sinusoidally. And this perfectly works, as you can see here on the next slide. So this is this topology. Switches are pretty small in area because they only need to operate in 1/6 of the period here, as you can see, and they are operating only with a low current. So this is really a very interesting topology. It's bidirectional and it's buck boost because, of course, we can step down here or we can keep this switch in the on state and then we just boost up here the voltage. So this is something which, at least to our knowledge, has not been published so far. There is some key ideas which are mentioned in literature, but this is something which I think from the level of complexity would be a very interesting topology, also for battery charging, for example. Swiss rectifier. I have always been asked, now you are in Switzerland at ETH, you know, for 5-10 years, and where is this rectifier? Because all people talked about the Vienna Rectifier. So I needed to come up with something which is tied to Switzerland, or Zurich at least, where I'm living. And you see, this is again this topology. And now you say, okay, we managed to integrate this into the front end part. But why not use the buck output stage, combine it with this, and just have two buck stages here, and the current in between the two buck stages, so there's the lower half here is again a buck stage, the current is what we inject back here, so we shape this upper current, we shape the lower current, and Kirchhoff's current law just ensures us that the third current is also sinusoidal. And this perfectly works. You can see here, oh, my image is missing here. Okay, there should be a rectifier, but yeah, disappeared seems. But the important anyway is here the 99% efficiency, even close to 99.3% efficiency. So you can achieve here a very, very nice efficiency, and also in a reasonable volume, I would say. Now we had the boost, which was the Vienna. Now we had the buck, or partly already buck boost, but let's think of buck boost type topologies also. Because this would be actually the one which would be especially suitable for battery charging. And you remember this topology. It's the two-level, which was not so favorable because it had higher input current ripple here, but still you could say, okay, I mean, it's a simple topology, it's bidirectional, so it's nice. But my output voltage is always higher than the mains line-to-line voltage. So this is something, and as a three-phase person, you are always tied to the star point. You are aiming for symmetry. And this is something which would then, I mean, make you think only kind of symmetric here. In the midpoint, this would always be your reference point, and you would generate voltages around the midpoint. But how about taking the negative bus here as a reference, and I'm referring here to Slobodan Čuk actually, who proposed something like this in 1982, so this is when I started in power electronics. Still remembering this, you can see you could generate your voltages here with reference to DC minus. And then if you have a very high voltage at the input here, just put a buck stage in front in each phase and build a buck boost converter here in each phase. And this is something which is extremely nice and very nicely works. So Michael Antivachis, PhD student, he verified this with the gallium nitride converter. You can see here, this is the voltage of the mains, and we are generating this output voltage level here. So we have partly buck operation, and then we have boost operation here, and the current is nicely sinusoidal here, and this can not only be used as a rectifier, but it can also be used as an inverter system. So now we covered buck, a boost, and buck boost, and the main limitation we still have is isolation. Isolation is missing. Now, you could do it in a highly complicated, but still very nice form. I mean, Vlatko Vlatkovic at CPES, for example, in 1994, has built something like this. We tried to further optimize it. There is an optimal modulation, keeping the current at minimum, ensuring soft switching here. This would be this primary side current, and you see the voltages at this side and at this side. This would be voltages of this shape. This is an equivalent circuit. This is the stray inductance of your transformer here, and you can see this is a dual active bridge concept. And you can shape very nicely your current to be sinusoidal here at the input, and you can transfer a constant power to the output, and you have a bidirectional feature here. So this is very nice circuit, very complicated. For this reason, I put the books here, perfectly suited for a PhD thesis, keeps you busy and thinking for hours. Here you can see the prototype. Power density, again, this was the figure we were always aiming for. It's something like 60 watts a cubic inch. And important here is this number up here. It's 98.9, very close to 99% efficiency. So this is something which this topology would allow you to achieve. And I think this is a very nice performance. And here you can see the input current, which has a little bit of ringing superimposed, but still it's a very nice current quality. And what you can see here, and this is really from first measurements of Lukas Schrittwieser, who did the PhD thesis on this topic, that we are really here scratching the 99% limit. But there is more. It's a possibility to do it matrix type, but you could again think beyond a bit. And you would say, okay, this is a boost type rectifier, 2-level. We have seen it now 3 times. But then you say, okay, I maybe should analyze what voltage I have across those filter inductors. This is generating a current ripple. And if you plot this voltage, and it's done here, then you would say, this is pretty much of a switching frequency voltage. Couldn't we really utilize this in order to really have a power transfer to a secondary side stage, which would again be a 6-switch circuit, which kind of duplicates the PWM with a little bit of a phase shift. Again, a dual active bridge concept here. So it's dual 3-phase active bridge PFC rectifier with integrated isolation. And if you would like, you even could tap off power here from these DC ports. So basically you have a 3-port structure where 1 port here is isolated. And this is a very nice feature and very nicely works. For the moment, we only have done simulations, but you can see here the input voltages, here is the input currents, and the output power, the power which goes to the output. It's fluctuating in the phases, but the total power which is delivered is constant. And the very nice feature is you have only 1 voltage drop here on the primary side and the same on the secondary side. So this is a very nice property, I guess. Okay, overall summary. And I think I managed, I have 2 minutes still. What is the conclusions? There is several, I call them black belt PFC rectifier topologies. So this is really the core which you can use, which is flexible, not too complicated, robust, I guess. Efficiency can be achieved here with a 99.5 limit. Even we have first studies in our lab which show that this is possible. 99% has nearly been demonstrated already with this isolated topology of Lukas. And the compactness, it's 10 to 12 kilowatts a liter, or something like 200, 250 watts a cubic inch. This is what you can achieve. And of course you ask, what would be possible further improvements? I mean, a higher number of levels. This is 2-level. We found this not to be the best. 3-level is better, but you would say, okay, why not go even higher number of levels? I mean, one issue which I would see here is if you have a failure here, then without redundancy, you are lost. So if you go really high number of levels, there will be lower reliability or lower mean time to failure. You can nicely predict this actually. And then without the fault tolerance, you would be lost, I guess. It's also well known from medium voltage. Further improvements continued, faster switching, the experience of the little box. We built the little box 1.0, which was going into the finals, 250 kilohertz to 1 megahertz. Power density, 140 watts a cubic inch. In the meantime, we have a little box 2.0, 140 kilohertz, high ripple of the input inductor, not variable switching frequency, partly hard switching, 240 watts a cubic inch. So you need to think of the system and not just of the power semiconductor. I think this is the message here. And what is very important in future is faster design and development, and this will need trade-off studies. If you move around here, all different things will change, cost will change, efficiency will change, power density. So this is something really important. 9 seconds left, 10 even, okay. Power electronics, future development. I think this is a very mature area already, some 10 watts to 100 kilowatts. System applications will be very important here. But I think there is plenty of room at the top, medium voltage, medium frequency, solid state transformers, for example, and there's plenty of room at the bottom. I think you know this, the quotation from Feynman, which would mean for us power supplies on chip. Development of power electronics continued. I think we are running through a technology S-curve. The question is, what is this part here? In my opinion, it's passives. Switches are very much driving, of course, the development, but are as good such that we can, with the magnetics we have, not really utilize them. Advanced packaging being very important. Advanced design, meaning efficiency and power density and cost considered at the same time, and knowing about the sensitivity against each other. And I think measurement technologies, not to forget, it's not really mentioned, but we not only need to design for manufacturing, but we also need to design for measurement and testing. And this is, I think, very important. I would see the oscilloscope to be built in a power converter maybe in future, at least in those converters which you use during development. And that's it. Thank you very much.
Okay, questions? Please step up to the mic and please state your name and affiliation, please.
I'm Britt Singh from John Deere. So I just wanted to know that when you're putting multiple switches and all that, so passive parameter and stray parameter consideration would be very, very important. Could you speak to that? Like stray inductance, stray capacitance and all that will play very much important role.
You mean in the combination of the semiconductors, and if the arrangement of the semiconductor is not a simple bridge like, but you have some extra switches, yes, and you have larger commutation loops, this is what you would mean?
Yes, that's correct.
Yeah, I think you are perfectly right, but I mean, in the demonstrator systems which we are building, we are using discrete devices and can very nicely manage actually to keep those commutation loops very small. Over voltage is in the range of 20 to 50 volts. So with a 400 volt of DC, which you need to turn off, I think this is pretty fine. And if you do a power module, I think similarly you could achieve a very good performance. There are several power modules which have been built for the Vienna Rectifier, and I think they are all working properly. So I think you would not need to be concerned about these commutation loops with a bit more of complicated switch arrangement. I think in future I would see the commutation loop capacitor, so which really closes the loop with very low impedance. I would see this integrated in the power module in future.
Okay, thanks.
Thank you.
One more question, please.
Ralph Gelke from Design and Electronic. Professor Kolar, you mentioned briefly at the end this measurement technology embedded or integrated oscilloscope. Yes. In the digital world. We have for many years now embedded instrumentation. Do you think of something like that?
Thank you very much. It's an excellent question. I think, once we built a little box, we assembled it together, but we couldn't measure anything. So this is not nice, I guess. Because you just can't trust that the whole thing works and there's no over voltage, no over temperature inside. And I think this is a situation, the more and more we integrate, the more and more we should still have access to some key points of our circuit, meaning voltage and current measurement or temperature measurement. And I think this is what needs planning in the design stage already. And I think you could have probes which are powered from your circuit just in the development sample. You remove it afterwards. Even your switches could maybe support such measurement. I think this would be a possibility, or gate drives which would be special just for development in order to have access to such key waveforms which are determining the reliability of your circuit finally. I think a second one which I would see is that the measurement and the simulation would need to be decoupled as they are today. I mean, you have a model, and if you measure, you could input the data into the model, adjust the parameters of your model, and have the digital twin, which is so much mentioned today in all different kind of areas, but why not also in the power area?
You know, last year rep session, we had a topic called, I think, have we invented all the topologies? And clearly, it's, the answer is no, so thank you very much.
Thank you.
Great job.